Hi, I'm Arthur Wang. This is my Lab 2 motion of a falling object lab report. So the experiment. We will observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. We will then construct an observed position versus time graph through the use of tracker to analyze the video. Then, we will construct a predicted position versus time graph by making two separate computational models that apply the concept of Newton's second law, with one having just the force of gravity and one with both the force of gravity and the drag force, respectively. And then finally, we will compare the observed and predicted position versus time graphs. Alright, so the subject of my experiment. My experiment examines the position versus time function of a ball being dropped from a meter height. The ball seems to speed up as it falls, though it cannot be determined for certain if the ball is subject to air resistance without further data analysis. It falls towards the floor, so the force of gravity is likely to be present. And I analyzed before the ball bounces, so right when it hits the ground. That's where it ends. So Newton's second law and the turbulent drag force. So we have V final equals V initial plus F net divided by mass times delta T. That's our Newton's second law of velocity update. The position update, R final equals R initial plus V average times delta T. These are both derived from Newton's second law. And then for the turbulent drag force, we have the formula F force. The drag force is equal to the drag constant times V squared times V hat. Alright, so this is my tracker data. You can see that it's a curve, and we have it starting at a position of 1 meter, and then ending up on the floor at 0 over the span of 0 to 0.517 seconds. Alright, so applying Newton's second law, just gravity. So my computational model code for just gravity applies Newton's second law in updating the position and the velocity. The time interval was chosen based on the tracker data for consistency, so 0.517 is the maximum time. The velocity update uses the equation V final equals V initial plus F net divided by mass times delta T, so that's right here. And position update uses R final equals R initial plus V average times delta T, so that's here. Alright, so applying the Newton's second law of gravity with drag force. This one's a little bit more complicated. So my computational model code for gravity with drag force applies Newton's second law in updating the position and the velocity as well. But the drag force is calculated by creating a variable, which I put as velocity underscore mag, that stores the magnitude of the vector, and the drag constant is found through trial and error to make it match the observed start and end data points for the tracker data as closely as possible. So by subbing in values for B, I was able to kind of guess this value through trial and error, so that it would basically be start at 1 meter and then end at 0 meters in height. Okay, so the time interval is also chosen based on the tracker data for consistency, so 0.517. We use this formula, so FD equals negative B times V squared times V hat, and then you had to put the code equivalent, which is here, negative B times J hat, which is just the equivalent of V hat in this lab. And after finding the B value to try and error, that's how we use this equation. Then for the glow script model, this is actually what they show. This is the one on the left. It shows just gravity, and then this one on the right has gravity and the drag force. So you can see there's a drag force in the opposite direction. And you can see that this one has a constant slope, and then this one has a decreasing negative slope. Alright, so tracker and model comparison. So this is all the data. It was pretty painful getting all the data points from GlowScript because the text box where you copy and paste from is really sensitive. But you can see from the graph, the model with just gravity ends up way below. It was like negative 0.25 or negative 0.3 meters, whereas the model with gravity and drag ends up far closer to the observed data. It may not be closer at the start or around this area, but it does end up closer because it has a more accurate slope over time. Alright, so the GlowScript model comparisons, what does it mean? So the model with gravity and drag force predicts a terminal velocity as the velocity approaches a value around negative 3 meters per second, which can be seen right here. It doesn't end up far below, or doesn't end up just keep decreasing. The model with just gravity does not predict the terminal velocity, as the velocity has a linear slope, as the force of gravity is constant and is the only force depicted by this model, with the one with just gravity. So what if we're asked to determine if the object was initially thrown downward, would the terminal velocity in the case be same or different than if it were just dropped from rest? In this case, it would be the same, though it would reach it earlier. So the model with gravity and drag force approached around -3 meters per second as a result of the formula for the drag force being balanced against the gravitational force, where the difference in magnitude between the two forces becomes more and more negligible, as in they cancel each other out. Thank you.